This section is still continuing with regular structures. It's read-only memory, somewhat deprecated, but the architecture of the read-only memory certainly is still quite relevant. So in this particular case, we have an n-bit row decoder and an m-bit column decoder, and it'll decode this array to one of these memory cell elements, which will then be put on the D-out pin. So some in-class assignment questions. How many functions of n plus m variables could you implement in the ROM from the previous page? And then how many functions of n plus m variables could you implement in the ROM on the previous page at one time? And the other question you might ask yourself, why is there a DN? So with respect to the regular structures continuing along, it certainly illustrates an organization common to a wide variety of semiconductor memory. We have the row address, the column address, and the output of a selected cell. And the other point here is that the memory could be organized in either single bits as shown there, or grouped together to form bytes or words. ROM memory is extremely dense. The data content of a cell is simply the presence or absence of a transistor. So these are masked programmable ROMs. That means the transistors are placed when they're being manufactured, and in that case you better never want to change the program. A selected transistor would then pull down a previously pre-charged line to give a logical 0. If there's no transistor, the pre-charged line would just retain its charge and provide you a logic 1. So data lines in the arrays are typically quite long, and the cell transistors are very small. And what that basically would mean, if you just combine them directly, you'd have extremely large, long time to discharge a data line. And you want to be able to interrogate the memory in a reasonable amount of time. And we have small voltage changes, so that basically requires some sense amplifiers, and that's usually going to be some type of a differential sensing to drive the line to VDD or ground, the output that is. There's other layout issues. We already mentioned the small devices driving large loads. Other concerns would be optimizing area, where there's a trade-off between rows and columns. And one thing that can happen there is unpopulated columns could also be removed, or unpopulated rows could be removed. And then in that case it basically becomes what we noted before, that programmable logic array. The same issues, some of the same issues rather, are the case also for flash type devices when they're used in a ROM type of fashion. So these are programmed by, the ROMs that is, are programmed by selectively placing transistors fixed at time of fabrication. And perhaps that's a bit of a new notion to some of you anyway. So this primarily makes the use of ROM only reasonable for extremely large volumes, or perhaps space applications where the program's not going to change and you want some rad hardness there. Field programmable ROMs are usually much more attractive for many applications, and these are sort of flash memory based. They're not really ROM, but they are persistent. So here's an example where a ROM is going to be 4 words and they're 6-bit wide. And it's sort of represented down here as a dot notation showing where the transistors are placed. And this is a higher level schematic showing all the gates where the transistors would be actually placed. So here's our decoder, and there's our outputs. So in this particular case, if you had word 0, so that's A1 and A0 both equal to 0, you'd end up outputting a 0, 1, 0, 1, 0, 1. And that's sort of illustrated in this particular case, where A1 is equal to 1 and A0 is equal to 1. It turns on this line. So this, in effect, turns on this transistor, turns on this transistor, and turns on this transistor. So this line that was previously pre-charged is pulled down to 0. This line, which doesn't have a transistor on it, remains at 1. And the output is just a complement of that, and that would be word 3. So here's what the layout-ish kind of thing would look like. In this particular case, we're decoding to one of these metal lines. Let's say AB00 or AB01 would decode here. And in this particular case, if you do decode here, you'll turn on this transistor, discharge this line, not discharge this line, discharge that line. So in a sense, it's kind of NOR-like. These two transistors are in parallel, but only one of them will be on at a time. And you might ask yourself, what are the outputs here? And hopefully you can identify this would be an output line, this would be an output line, this is an output line, this is an output line. So the placement of the transistors basically provides you the memory content. Here's the scenario where it's flash-like. So transistors are everywhere, but it's a floating gate. And when it's programmed, you either put charge or take charge off of the floating gate. And if you charge up this floating gate, you in effect can't turn it on. So it's as if this transistor is no longer present. In this particular case, if you activate this line, you would turn on this transistor. Since its floating gate it doesn't have charge on it, and you discharge that line, and you would not be able to turn on this transistor, so this line would stay high. So once programmed, they stay off. And then we're going to look at a little bit of static memory, or SRAM. And these again are regular structures. The basic cell is a cross-couple latch, so it needs a power supply to maintain its state. It's volatile memory. You turn the power off, it loses the content of the memory. We're going to look at both read and write functions. We're still going to have that notion of row and column decoding, and that'll allow us to access a cell or a group of cells. So here's our basic cross-couple latch here. Bit and bit bar are pre-charged. In this particular case, we're looking at a read. So these lines are pre-charged, and then they're going to be conditionally discharged once we strobe the word line. So word is strobe, bit or bit bar is conditionally discharged. So initially they're at the same voltage, let's say VDD by 2, and then when the word is strobed, they're either going to be, one of them is going to be pulled low and one of them is going to be pulled high. So that'll also allow for some differential sensing. On the write operation, we put the data on the bit line, and we put data bar on bit bar line, and then we just tend to overdrive that cross-couple latch, overpower it when word is strobe. So the latch is then overwritten. Here's an example of some old versions of some layout of 6 transistor SRAMs, and at this point in time we'll take another break.